Okay, good morning all. So let us continue. This is lecture 3. So far we have seen some examples of non-linear spaces, and I did not verify that those are indeed the norm, but you should try to verify for all of those. Uh, Today, let me start with defining what is known as Banach spaces. So definition. Non-linear space X is said to be a Banach space if it is a complete non-linear space. So any complete non-linear space is said to be a Banach space. So what do we mean by complete? So recall X with norm. This is complete if every Cauchy sequence in X converges to some point in X. More generally, this is defined for any metric space. A metric space is said to be complete if every Cauchy sequence converges to a point in X. So any non-linear space is also metric space. So this is with respect to that metric. Now what does this mean? So again, what is a Cauchy sequence? A sequence Xn is a Cauchy sequence if given any epsilon positive, there exists some natural number n naught such that norm of xn minus xm, this is less than epsilon for all nm bigger than equal to n naught. So at least you would have seen this for a sequence of real numbers. We write mod of xn minus xm less than epsilon for all nm bigger than equal to n naught. Here mod is replaced by norm. And more generally for metric space, it is distance between xn and xm less than epsilon. So this is the definition of Cauchy sequence. And we already have seen that sequence xn converges to x if given epsilon greater than 0, there exists some n naught such that norm of xn minus x is less than epsilon for all n bigger than equal to n naught. So we'll see later that this completeness is a very important property. So if a nonlinear space is complete, then it is given a name as Banach space. Now, what are some examples? So R with the usual norm given by absolute value, this is a Banach space. Right. So this is a standard fact that uh, in real numbers, if we take any Cauchy sequence, then it must converge to a real number. So this you would have seen in course on real analysis. Now, if I have any and similarly C also will be a Banach space, and if we take any of these space we denoted as LPN, this is also a Banach space. For 1 less than equal to p less than equal to infinity. So we have defined L infinity n also. So these are all Banach spaces. So here what you have to see that if you have any Cauchy sequence in LPN, then if you look at the component, the first component, second component, and nth component, then you get a sequence of real numbers or complex numbers, and that will again be a Cauchy sequence. And since we know that R and C are complete, so that Cauchy sequence will converge to some for each component, and then you prove that the original sequence in this Rn will converge to that vector in Rn or Cn. So this follows from the previous result. What were the other examples we have seen? So we so these sequence spaces are all Banach spaces, and
Sir, Rn or Cn are also
sorry,
Rn or Cn with Euclidean norm.
yeah, that is a special case of what I have said in 2, right?
Yes.
If you take p equal to 2, then you get the Euclidean norm, right? So I have given in general that for any p bigger than equal to 1, this is a Banach space. Yeah, also if I take this for any say compact topological space, so this Ck is a Banach space. For any compact topological space K. So CK, remember that the norm here is given by the sup norm. So norm of F is equal to the supremum of mod F of T, T belonging to K. So here again, if you want to show the completeness, then if you take any Cauchy sequence of functions Fn, then you have to show that it will converge, right? So let's briefly see. So suppose Fn is a Cauchy sequence in Ck. Now let epsilon greater than 0 be given. Then there exists n naught such that the norm of Fn minus Fm, this is less than epsilon for all Nm bigger than equal to n naught. This is the definition of Cauchy sequence. Now, if we take any t, if t is any point in K, then mod of Fnt minus Fmt, this is less than equal to norm of Fn minus Fm, right? Because norm of Fn minus Fm, that is the supremum of this for all t in K. So for any t, this is less than equal to norm of Fn minus Fm, and which we have seen that is less than epsilon for all Nm bigger than equal to n naught. So this will imply that this Fnt, if we look at the sequence Fnt, this is a Cauchy sequence in R. So now we get a Cauchy sequence in R. So we will use that R is complete. So therefore it will converge to some point. Since R is complete, ठीक है ऐसा हो ये 11 से 12 अभी क्लास होती है ऐसा ना करियो हमारी सब मुझे कल वो सफाई वाला आता ही नहीं तो करने के लिए दिया ना जब आपको जब समापन So since R is complete, this Fnt converges to a real number so we can define, so therefore define f of t is equal to the limit of this f and t. So now we have defined a function f. Now we claim that this sequence fn, this will converge to f in this nonlinear space ck. So what you have to show, first of all, you have to show that this f is continuous. So that f is continuous on k. Hence, you will get that this f belong to ck. And next thing, you have to show that norm of fn minus f, this goes to 0 as n goes to infinity. So once you prove this, then that will show that this fn converges to a function f in ck. So this you can try to prove these facts. So next is yeah, these capital LP spaces are again Banach spaces. So maybe let me just mention that. Capital LP is a Banach space. P greater than equal to 1. So these again maybe I'll give as tutorial problems, and it can be discussed in the tutorial class. So also you should see something which is a non-linear space but not a Banach space. So we have seen this example C00, which is a subspace of L infinity. So C00 was all x equal to x1, x2.
Sir, for
Xn
the
is
third example, like for CK, do we need K to be compact only? Like if K is non-compact, then CK like need not be this thing Banach.
no. The problem is that if K is not compact, then CK is not a non-linear space, right? So in that case, you can look at only bounded real valued continuous functions.
Okay. Okay.
But if K is compact, then we take any continuous function, it is automatically bounded. So because to define this supremum of mod f of t, this should be finite, right? So that is why I have taken compact. Otherwise, I can take CB of any topological space Y, and that is also a Banach space.
Okay.
Okay. So yeah, that again you can check. The proof will be similar if you assume that it is the a space of all bounded continuous function. Then the way I have done here, the same way you can prove that it is complete. So this C00, which are sequences which are eventually 0. Say these exercise a real number or complex number. So what can you say about this? Is it complete or not? This is not a Banach space. So can anyone tell why this is not a complete nonlinear space?
You can take a like a sequence of sequences where the ith sequence is of the form 1 half 1/4 dot 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 up to half to the power I and then all zeros.
Okay.
So this will be Cauchy sequence, but it will converge to like a sequence outside C00. Like it will converge to the sequence 1 half dot 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 up to half to the half to the power n, and it will go till infinity.
You are taking the sequence 1/2 up to 1/2 to the
So the
n.
ith sequence is 1
Right.
half dot 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 up to half to the power I and then all zeros. So ith sequence has I plus 1 non-zero entries, and then I take the collection of this sequence, these sequences which are Cauchy, but they converge to a sequence which is not eventually zero.
Right. Oh. So yeah. So in fact, this C00. Oh, this is not a closed subspace of this, right? So, oh, let me write. Note that C00 is not a closed subspace of infinity. So if I have any closed subspace of Banach space, then it is also Banach, right? So maybe let me write this. So any closed subspace of a Banach space is also a Banach space. So on a subspace, you know that we take the norm restricted to that subspace. So it's also a Banach space. So this is because any closed subspace of a complete metric space is complete. So this is follows from the fact that any closed subset of a complete metric space is complete. Right, and this fact is again easy to prove because if you take any say closed subset of a complete metric space, now suppose you take a Cauchy sequence in that, then this sequence is also in the bigger metric space. So it is a Cauchy sequence in the complete metric space. So because this is complete, any Cauchy sequence must converge. So what we will get is that the sequence xn will converge to some point x in say x is a complete metric space and y is a closed subset. Then the sequence xn will converge to yn will converge to some point x in capital X. But that will imply that x belongs to the closure of y, but y is a closed set, so therefore it must be a in y. So we'll get that this y is also complete. So, but if it is not closed, then it cannot happen, right? So in fact, any subset of complete metric space. If it is complete, then it must be closed. So, okay, so and later we will also see that in fact, if you look at this C00, then you can write a basis for this. If you write E1, E2, E3, where EI is the sequence where the ith term is 1 and all the other terms are 0, then it is easy to see that that forms a Hamel basis for C00. So this C00 has a countable Hamel basis. Now we will show later that if we have any infinite dimensional Banach space, then it cannot have a countable Hamel basis. So the Hamel basis is simply the basis that you study in linear algebra. So it's a linearly independent set which spans the vector space. So in fact, we cannot define any norm on this C00 which will make it a complete nonlinear space. So that we'll see later, but here for this example, you can like prove it directly also. Similarly, if I take the space of all say polynomials and define norm on that, then that will again be the incomplete nonlinear space. So it will not be a Banach space. Okay, maybe you will see more examples later. So
So, but
now
LPN
let's
also has a countable basis, like LPN, but that
no, it does not have countable basis.
LPN, like we can take the standard basis for n-dimensional vectors.
But that will not be a Hamel basis for LP.
Uh, uh, so Hamel basis, like for LPN.
So you are maybe confused with basis. There are different notions of basis, right? So when I am
Right,
saying
right,
Hamel
right. So
basis,
I was talking in terms
that
of
is
the vector space basis.
yeah. In terms of just vector space structure, it is not a basis. So for example, if you take L infinity, right? So let's look at this. So question is E1, E2, En Hamel basis for, let's say, L infinity. So do you think this is a Hamel basis for L infinity?
We can just take like finitely linear combinations. So
Yeah, see,
maybe
when we talk about basis in a vector space, basis of a vector space, then that means that every vector can be written as a finite linear combination of vectors from this basis, right? Now, if you take only finite linear combination of vectors from this E1, E2, En, this is true even for LP, you can do the same thing. Then you will get only finitely many non-zero terms, right?
we can try 1 1 1 1 1 1 this
Right.
way.
So for example, so the answer is no. And simply you can say that the sequence 1 1, the constant sequence 1, this belongs to L infinity, but it is not in span of E1, E2, so on. Because if you assume that it is in the span, then it has to be C1 E1 plus C2 E2 up to some Ck Ek, right? So anything in the span is of the form some finite linear combination of these vectors, but that will give you after some stage all the terms are zero. So this cannot be, right?
No,
Is it
actually, I
clear,
was
Dheeraj?
talking about L, like the n-dimensional vectors only, like L infinity n or LPn, wherein we
Yeah,
just
so
have this finite
that,
dimensional
that is
space
just
that
a
have a
finite.
finite basis.
Yeah, you are saying if I take a LPn.
Yeah, so that will be countable also, but it's Banach.
No, but that is finite dimensional.
Oh, okay. So if we have an
What I said
infinite
is that
countable set of Hamel bases, then it's not Banach.
yeah, countably infinite it cannot have.
Okay, so it can either have finite or after that it will go uncountable.
Exactly. So that is what I said before is that if there is an infinite dimensional Banach space, then it cannot have a countable Hamel basis. Finite dimensional, see, always, in fact, we will see that uh, on finite dimensional, it will always be complete. So it is always a Banach space. So any finite dimensional nonlinear space, so that is the Banach space. Okay, so okay, now we will talk about bounded linear operators. So let x and y be non-linear spaces over the same field F. F is either R or C. So if we have two vector spaces, then you know what is the meaning of a linear operator. So first of all, a linear operator from x to y is a map T from x to y satisfying T of alpha x plus beta y is equal to alpha tx plus beta ty for all. Oh, let me write better. I should write some T alpha x1 plus beta x2 is equal to alpha tx1 plus beta tx2 for all x1 x2 in x and for all alpha beta in f. So this is just a linear transformation that you study in vector space in linear algebra. So on vector space we can define a linear transformation. Now what is the meaning of and we have some notation. So we write Lxy. This is all collection of all linear operator T such that T is a linear operator from X to Y. And this is a vector space Lxy is a vector space with the usual vector space operation. So you can define sum of two linear operators and you can define scalar multiple of a linear operator. That is again a linear operator. So though this you have seen in a linear algebra, that you can look at a new vector space, which is the vector space of all linear transformation from one vector space into another vector space. Now, what is the meaning of a bounded linear operator, or also some terms that you should be familiar with? Uh, what is kernel of T? This is all x in X, such that T of X is equal to 0. This is a subspace of X, and range of T this is all T of X, X belonging X in X. This is a subspace of Y. So these are the kernel and range space, and if I have any linear operator from X to Y, it is called an vector space isomorphism if it is a linear transformation and it is also 1 1 and on 2. So that is equivalent to the kernel being the zero space and range of T being the full space Y. So these things you should be familiar with. Now, what is the meaning of bounded linear operator? So, definition: a linear operator T belonging to Lxy is said to be a bounded linear operator if there exists some constant m such that norm of Tx, this is less than equal to m times norm x for all x in X. So note that these two norms are different, right? So norm of X, this is the norm on the norm linear space X, and T of X is an element of the norm linear space Y. So here we take whatever the norm is given on Y. So we will not always write this subscript Y and X. It should be clear from where these vectors are. So if we have that there is some constant m, when I write there exists m bigger than 0, of course this has to be a real number, so it has to be finite. So there is some real number m such that norm of Tx is less than equal to this constant times norm x for all x. So we will write notation bxy This is the collection of all bounded linear operators from X to Y. So note that Bxy is also a vector space. So we said that Lxy is a vector space, when this Bxy is actually a subspace of this L of xy. So, why is this a vector space? So you know that if you have any two linear operators, then any linear combination is again a linear operator. So you have to only show that it is bounded, right? So if T1, T2 belongs to Bxy and alpha, beta are scalars, then we have to see that alpha T1 plus beta T2, this is also in Bxy. So we already know that alpha T1 plus beta T2, this is in Lxy. And if we look at alpha T1 plus beta T2 of X, then what is the norm of this? This is same thing as alpha T1X plus beta T2X norm. And then by the property of norm, this is less than equal to mod alpha times norm T1X plus mod beta times norm of T2X. And T1 and T2 are assumed to be a bounded linear operator. So this is less than equal to mod alpha times some M1 norm X plus mod beta times some constant M2 times norm X. And then this is equal to some M times norm X, where M is equal to mod alpha M1 plus mod beta M2. So therefore, this will imply that alpha T1 plus beta T2 is a bounded linear operator. So this is easy to see. Now, okay, when these domain space and range space are same, then we'll write Bxx is denoted by just Bx. Similarly, Lxx is just Lx. So if we write Bx, then it is just so T belong to Bx means T from X to X is a bounded linear operator. Also, you see, if we take y to be equal to the field f. So the special case, if y is equal to f, then any t belonging to Lxf. So if I have any linear operator from x to the field f, this is called a linear functional, and we write x dash. This is same thing as all linear operator from x to v. So if I write x dash, this means the vector space of all linear functional. So this is x dash is the vector space of all linear functionals on X. And similarly, we can talk about bounded linear functionals. We write X star. This is the space of all bounded linear functionals. So that is, this X star is nothing but B of XF. We will see that this BXY, and then in particular this X star, this is also a norm linear space. So this, in fact, we can define norm of operator on this. So it is not just a vector space, it is a norm linear space also. So that we will see how to define a norm. So
Sir,
so yes.
and we also say that dual of this space of bounded linear functionals is also bounded linear functional.
Yeah, so yeah, I did not say this is also known as the dual of X. So X star is called the dual of X dash, that is also called dual in the vector space sense. So that is the vector space dual. Here we have norm linear space. So we have the space of all bounded linear functional, that is called the dual of the norm linear space X. Dual of the norm linear space. Yes, what was your question? Yes.
So if we take the dual of the space of all bounded linear function operators or functionals
Uh-huh.
on X, then the space is linear. Bounded means the space we get, that dual space is also linearly bounded.
No, no. So see, we have defined X star, right? X star, right now I only said that this is a vector space, but once I define a norm on this, then you can talk about the dual of this also, right? So that will be denoted at
Yes.
x star star. That is called the double dual, right? So that will be. But right now I have not defined any norm on this x star. So I am not saying what x star star is. So you can take dual of for this non-linear space also, x star also, right? So again, that will be all bounded linear functional on x star. So that will be a t from x star to f such that t is linear and t is bounded. Was that your question?
Yes.
Okay. So for that I have to first define a norm on this. But first let's look at an important property of bounded linear operator.
Can we have an example of unbounded linear operator?
Yeah, that also we will see. So we will see examples of unbounded. For example, unbounded linear functional. Can you think of any non-linear space and an example of unbounded linear functional? So if you want, I can give that first. So example of an unbounded, which means which is not bounded. So unbounded linear functional. So you have to give a non-linear space and then define a linear functional which is not bounded. So let let us take x is equal to let's write okay, maybe I can take easy example. So t pr I'll write this is the space of all polynomials with real coefficients. So you know that any polynomial is a continuous function, and it is also differentiable. So what is the norm that we'll take here? Uh, okay, maybe I'll write p of 0 1. So all polynomials on the closed interval 0 1 with real coefficient. So we take this space, and you can define norm of if I take any polynomial, let's say f of t, you can just look at the supremum of mod of f of t, t belonging to 0 1. Right, any polynomial is a continuous function. So you take the sup norm. So this will be finite. Now I can define t from x to r Okay, let's try to define it like this. So T of any polynomial f of t let's look at this is equal to f prime at 1. So is this t linear? If you take any two polynomial ft and gt, then t of ft plus gt will be equal to f prime 1 plus g prime 1. So yeah, so this will be linear. And is it bounded? T is linear.
No. You can take x to the power n. The derivative at 1 is going to be n.
Right. So I'm saying that t is not bounded. This is because t of, if I take the polynomial t to the power n, then that is equal to n. Right. So if it is bounded, then that will mean that t of so if t is bounded, then norm of t of f this is less than equal to some m times norm of ft. So if you look at t of t to the n, this has to be less than equal to m times norm of t to the n. Now, what is the t of t to the n? This is equal to n. So this will imply n is less than equal to m times. What is norm of t to the n? This is the supremum of t to the n for n for t belonging to 0, 1. So this is just 1. So this will imply that n is less than equal to m. So this norm is equal to 1. So this is true for all n, which is not true, right? So a contradiction. So yeah, you can have unbounded linear functional. And later, in fact, we will show that for any infinite dimensional non-linear space, you can always define an unbounded linear functional. So that is something we'll see how to like construct an unbounded linear functional for any general infinite dimensional non-linear space. Okay, I think it is time, so I have to stop here. So in the next class, we'll see the theorem that I was saying. Maybe I'll just state that theorem. So what I was trying to say is that if T is any bounded linear operator from X to Y, then we have some equivalent condition. So T is a bounded linear operator that is equivalent to T being continuous. So because X and Y are also topological spaces, so we can talk about continuous function. So T is continuous function, and that is equivalent to T being continuous at 0. So this is a vector space, so we can talk about continuity at a point, let's say 0. And if T is continuous at 0, by using linearity, we will be able to prove that T will be continuous at all points in X, and that is equivalent to bounded. So bounded linear operator, we can also say that it is continuous linear operator. These are same concept. Another thing is that okay, so why is this T called bounded linear operator? So you should not be confused that when I say T is a bounded linear operator, this does not mean that as a function it is a bounded function, right? When you study about functions, say functions from R to R, we say a function is bounded if its image is a bounded set, right? But that cannot be true for a linear operator, a linear transformation, right? So what we mean by bounded is that it maps a bounded set to bounded set. So T being a bounded linear operator is also equivalent to, if I take any bounded subset of X, then its image is a bounded subset of Y. So that is the reason that it is called a bounded linear operator. So after that, we will define the norm of T if T is a bounded linear operator, and then we will show that this actually becomes a norm linear space, and then we'll see some other things. Okay, so let me stop here.
Thank you, sir.
Thank you.
Thank you, sir.
And also